Out in the cold, dark reaches of our solar system, beyond the familiar planets, and even past the orbit of Neptune, lies a world so strange and enigmatic that it defies everything we thought we knew about the outer edges of our cosmic neighborhood. This is Varuna, a hauntingly distant Kuiper Belt object shrouded in secrets, a celestial puzzle waiting to be unraveled. Picture a place where sunlight is so faint it's little more than a dim star in the sky, where temperatures plunge so low that ice becomes harder than steel, and where the very laws of physics seem to twist into something unexpected. What if I told you that this frozen relic floating in the abyss might hold clues to some of the greatest unsolved mysteries of our solar system? From its bizarre, elongated shape to the whispers of hidden activity beneath its icy shell, Varuna doesn't just challenge our understanding, it mocks it. Why does this tiny world spin so fast it should tear itself apart? What could explain the strange, flickering changes in its brightness that leave astronomers scratching their heads? And perhaps most chilling of all, why do some scientists suspect that Varuna isn't alone out there, that something unseen lurks in its shadow, tugging at it with invisible fingers? These aren't just questions, they're doorways into a cosmic detective story, one where every answer leads to deeper, darker riddles. That's exactly what we're diving into today. Over the next 25 segments, we'll uncover the most mind-bending mysteries swirling around Varuna, from its possible underground ocean to the eerie parallels it shares with legendary, undiscovered worlds like Planet 9. This isn't just about distant space rocks, it's about rewriting the story of our solar system's farthest frontiers, piece by unsettling piece. So strap in, because by the time we're done, you'll never look at the outer darkness the same way again. The unknown is calling, and Varuna might just be its most chilling messenger. Most objects in the Kuiper Belt are expected to be roughly spherical, shaped by their own gravity over billions of years, but Varuna laughs in the face of expectations. Instead of a smooth, planet-like ball, this distant world is stretched into a bizarre, football-like form, as if some unseen hand squeezed it from both ends. What could warp a celestial body like this? The leading theory points to Varuna's dizzying spin, rotating once every 6 hours, so fast that it flings material outward, bulging at the equator while flattening at the poles. At that speed, most objects would rip themselves apart, yet somehow Varuna holds together. But speed alone might not tell the full story. Some researchers suspect a violent past, one where Varuna was struck by another massive object, a collision so brutal it left the world permanently distorted. Picture two ice giants slamming together in the dark, their impact echoing across the void, leaving behind a twisted remnant that still carries the scars billions of years later. Others argue that Varuna's odd shape could hint at something even stranger, an internal structure less like solid rock and more like a loose rubble pile, its fragile body barely clinging together under the strain of its own rotation. And then there's the biggest question of all: why haven't we found more objects like this? If collisions or rapid spins are common in the Kuiper Belt, why does Varuna stand out as such an oddity? Every observation deepens the puzzle, leaving scientists to wonder if we're missing a crucial piece of the story, one that could rewrite what we know about the chaotic infancy of our solar system. One thing's certain: Varuna refuses to fit neatly into any of our models, and that's exactly what makes it so fascinating. If Varuna's strange shape wasn't puzzling enough, its surface adds another layer of intrigue, a darkness so profound it defies the typical glittering ice we expect from distant Kuiper Belt objects. While most bodies in this frigid realm reflect sunlight like cosmic mirrors, Varuna absorbs it, appearing as little more than a shadow against the blackness of space. This isn't just a quirk, it's a glaring anomaly that forces scientists to rethink what these distant worlds are really made of. One leading theory points to ancient organic compounds, thick layers of carbon-rich sludge coating Varuna's surface like cosmic tar. Over billions of years, radiation from the Sun and interstellar space could have baked simple molecules into complex, dark hydrocarbons, transforming what might once have been bright ice into something closer to asphalt. Imagine a world where the very ice we associate with purity has been corrupted into a sticky, alien residue, a relic of chemistry playing out in the slowest possible motion. But there's another possibility: space weathering. The Kuiper Belt isn't the serene paradise we once imagined. It's a shooting gallery of micrometeorites and cosmic rays bombarding objects relentlessly. Over eons, this constant barrage could have shattered Varuna's pristine ice into a fine, dark powder, scattering light instead of reflecting it. Think of it like sandblasting a mirror until it turns dull and hazy, except here, the process took 1 billion times longer, leaving behind a surface that's eerily unrecognizable from its original state. Here's where things get even stranger. Some researchers argue that Varuna's darkness might not be just skin deep. What if the entire object is fundamentally different, not a bright icy core wrapped in a dark shell, but something inherently shadowy from the inside out? This would upend our assumptions about how Kuiper Belt objects form, suggesting that the outer solar system could be littered with worlds built from materials we've barely begun to understand. And then there's the glaring question no one can fully answer: why is Varuna so much darker than its neighbors? If space weathering or organic buildup were common, we'd expect more objects to share its eerie gloom, yet Varuna stands out, a black sheep in an already peculiar family. Could its unusual orbit expose it to more radiation? Was it born in a different part of the solar system, carrying primordial stains from its origins? Every explanation raises new mysteries, proving that even in the deepest reaches of space, darkness isn't just the absence of light. It's a clue waiting to be deciphered. Varuna doesn't just move through space, it races, spinning faster than any object its size has any right to. While most worlds in the Kuiper Belt take leisurely rotations lasting dozens of hours or even days, Varuna completes a full turn in just under 6 hours, a speed so extreme it borders on the impossible. To put that in perspective, imagine a planet the size of Texas whirling so violently that its equator is flung outward, fighting against gravity's desperate pull to keep itself intact. This isn't just unusual, it's a cosmic red flag, screaming that something about Varuna's past or present defies the rules we thought governed these distant icy worlds. So what keeps Varuna from tearing itself apart? One compelling theory suggests it might not be a single, solid object at all, but rather two smaller bodies locked in a tight, messy embrace, a contact binary. Picture two massive icebergs slowly colliding in the void and sticking together like cosmic Velcro, their combined rotation sending them whirling like a mismatched top. This could explain both the speed and the bizarre, elongated shape we observe, two halves clinging together, forever on the brink of separation. But there's another, even wilder possibility. Varuna could be what scientists call a rubble pile, a collection of loose boulders and ice held together by nothing more than feeble gravity. Think of it less like a planet and more like a spinning snowball, constantly on the verge of bursting apart but somehow holding its form. If true, this would mean Varuna isn't just fast, it's fragile, a celestial house of cards where the slightest nudge could send its pieces flying into the void. The implications are staggering. If rubble piles are common in the Kuiper Belt, it would mean these distant worlds are far more delicate than we ever imagined, their structures shaped not by crushing pressure but by gentle, precarious balances. It would also hint at a violent history of collisions, where ancient impacts shattered protoplanets into fragments that later clumped together into these shaky, spinning aggregates. Yet even these explanations don't fully account for Varuna's extreme rotation. Some researchers speculate that a massive impact, one forceful enough to send the entire world into a dizzying spiral, could have set it spinning eons ago. Others wonder if tidal forces from a long-lost moon, since ejected or consumed, might have once whipped Varuna into this frenetic dance. Whatever the cause, one thing is clear. This tiny world is spinning secrets into the darkness, and each revelation pulls us deeper into the enigma of the outer solar system. Varuna's size suggests it should hold onto at least a wispy atmosphere, yet scans reveal nothing but silence, an eerie void where gases should cling. This is baffling, especially when compared to Pluto, its similarly sized neighbor, where nitrogen and methane dance in a fragile, ever-changing haze. So why is Varuna so unnervingly bare? One possibility lies in temperature, or rather the crushing lack of it. While Pluto's orbit brings it closer to the Sun at times, warming its surface enough to release frozen gases into a temporary atmosphere, Varuna lingers in deeper cold. Imagine the difference between a block of dry ice slowly sublimating in sunlight and one locked in a freezer, untouched for millennia. The darker Varuna's surface might also play a role, absorbing what little solar energy reaches it without retaining enough heat to vaporize its ices. But the plot thickens when we consider composition. Pluto's atmosphere isn't just a product of warmth, it's fueled by volatile ices like nitrogen and carbon monoxide, which turn to gas more easily. Varuna, however, might be dominated by heavier, more stable molecules, stubbornly refusing to sublimate even under ideal conditions. Picture two icy worlds side by side, one packed with fluffier ices ready to puff into gas, the other built like a dense, frosty boulder clinging to its frozen state. Then there's gravity, or rather, Varuna's struggle with it. Some models suggest its rapid spin might literally fling potential gases into space, a centrifugal force overpowering its already weak gravitational pull. Envision a child on a spinning merry-go-round, gripping the bars as hard as they can, except here, the child is a cloud of nitrogen molecules, and Varuna's whirl is too violent for them to hold on. The most haunting theory, though, is that Varuna once had an atmosphere and lost it. Seasonal shifts or catastrophic impacts could have stripped it away, leaving behind a frozen wasteland with only ghostly traces of what once was. If true, this transforms Varuna from a cosmic oddity into a cautionary tale, a glimpse of what could happen to other Kuiper Belt objects over eons. Yet the mystery lingers. If atmosphere loss is common, why do some worlds like Pluto still cling to theirs? The answer might lie in Varuna's dark surface, its composition, or even an unseen event in its past. Until we send a probe to this distant outpost, every explanation remains a shadow on the edge of our understanding. Amid Varuna's otherwise inky darkness, astronomers have spotted something that shouldn't be there: scattered pockets of dazzling brightness, glinting like cosmic sequins sewn onto a black velvet curtain. These bizarre patches reflect far more light than the surrounding terrain, creating stark contrasts that defy the object's uniformly shadowy reputation. What could possibly explain these radiant anomalies on a world so cold and distant that sunlight is 1,000 times weaker than on Earth? One compelling theory points to cryovolcanism, eruptions not of molten rock, but of water, ammonia, or methane ices. Picture a geyser on Earth, but instead of steam, imagine a plume of liquid nitrogen bursting from Varuna's fractured crust, freezing instantly in the vacuum of space and leaving behind a gleaming frost. These eruptions could be driven by residual heat deep within Varuna, perhaps from radioactive decay or tidal forces flexing its interior. Over time, these fresh ice deposits would darken under relentless radiation, meaning the brightest patches might be the youngest evidence of recent geological activity on a world we assumed was frozen in time. But there's another possibility: impact scars. When a meteorite slams into an icy surface, it can expose pristine material buried beneath the dark exterior. Think of it like chipping away at a charcoal briquette to reveal the shiny graphite inside. If Varuna's dark coating is just a thin veneer, even small impacts could puncture through, creating bright halos around craters. The strangest part, some of these reflective zones don't seem to align with visible impact sites, suggesting the ice might be resurfacing through cracks we can't yet detect. Then there's the wild card, exotic minerals. On Earth, we find salts and sulfates that gleam brilliantly in sunlight. What if Varuna hosts similar compounds forged in chemical reactions we don't fully understand? Certain hydrated minerals or crystalline structures could explain the patch's reflectivity, especially if they're concentrated in specific regions due to ancient subsurface flows or seasonal changes. But here's the real puzzle. Why are these bright spots so localized? If cryovolcanism or impacts were widespread, we'd expect a more even distribution. Instead, they cluster in isolated areas, almost as if something beneath the surface is controlling where and when the ice is exposed. Could there be underground reservoirs channeling material to specific weak points in the crust? Or do these patches mark the aftermath of rare, cataclysmic events that reshaped Varuna's surface in bursts? Every hypothesis leads to deeper questions. If the bright spots are young, why hasn't radiation darkened them yet? If they're old, why haven't they been buried by dust or debris? And most tantalizing of all, could these glimmers be hints of something even more extraordinary, like pockets of liquid water temporarily welling up before freezing solid? Until we get a closer look, these luminous enigmas remain Varuna's way of winking at us from the abyss, a silent challenge to unravel the truth hidden beneath its icy mask. Varuna's temperature map reads like a cosmic fever dream, pockets of unexpected warmth scattered across its frozen surface like embers refusing to die in a snowstorm. For a world so distant that sunlight is barely more than a faint whisper, these thermal anomalies make no sense. Standard models predict a uniformly frigid landscape, yet Varuna's reality is anything but uniform. Some regions hover just a few degrees above the surrounding chill, while others spike dramatically, as if the ground itself is generating heat. What could possibly be cooking beneath this icy shell? One tantalizing explanation points to subsurface friction, layers of ice grinding against each other as Varuna spins at breakneck speed. Imagine squeezing a rubber ball repeatedly in your hand until it warms from the motion alone. Only here the forces are planetary in scale. If Varuna's interior isn't perfectly rigid, its rapid rotation could generate enough internal movement to create localized hotspots, like a celestial version of rubbing your hands together for warmth in the dead of winter. Then there's the possibility of radioactive decay. While Varuna isn't massive enough to retain primordial heat like Earth, certain radioactive isotopes trapped in its core could still be decaying, releasing energy in slow, steady pulses. Picture a lump of uranium buried deep in Antarctica, quietly radiating heat for millennia, except Varuna's version might be laced with thorium or potassium, leftovers from the solar system's violent birth. But the real curveball, insulation. Varuna's dark, porous surface might act like a thermal blanket, trapping heat beneath layers of carbon-rich sludge. Think of how a black asphalt road absorbs sunlight during the day and stays warm long after sunset. Now scale that up to a planetary body where pockets of warmth persist in shadowed cracks and crevices, defying the icy vacuum around them. The wildest theory, though, involves chemistry. Certain mixtures of ice and ammonia can lower the freezing point of water dramatically, creating briny slush that remains semi-liquid even in extreme cold. If Varuna's subsurface contains these antifreeze-like compounds, they could generate heat through exothermic reactions as they shift states, like invisible underground furnaces flickering to life. Yet the most perplexing detail isn't just the heat, it's the pattern. These warm zones don't follow predictable distributions based on sunlight exposure or surface composition. Some cluster near the equator, while others dot the poles haphazardly, as if guided by unseen plumbing beneath the crust. Could there be underground reservoirs channeling warmth like geothermal vents, or fractures venting heat from depths we can't yet probe? Every explanation raises new questions. If friction or radioactivity were at play, why don't other Kuiper Belt objects show similar anomalies? If chemistry is the key, what stopped these reactions from playing out billions of years ago? And if Varuna truly harbors subsurface activity, how many other distant worlds might be hiding similar secrets? Until a spacecraft finally visits this icy enigma, these temperature fluctuations remain more than just scientific curiosities. They're breadcrumbs leading us toward a deeper truth about the dynamism of the outer solar system's forgotten realms. Varuna's dance around the sun holds a secret rhythm, one that shouldn't exist this far out in the solar system. While most Kuiper Belt objects follow predictable, lazy orbits, Varuna's path subtly syncs with Neptune's gravitational pull, like a metronome ticking in time with a distant drumbeat. This peculiar resonance defies the rules of celestial mechanics, where objects so small and distant should have long since drifted into chaotic, independent orbits. Yet Varuna's motion suggests a cosmic conversation with Neptune, one that raises a chilling question. How did this tiny, icy world lock into such an improbable gravitational tango? The math reveals the strangeness. Varuna completes 3 orbits around the Sun for every 4 Neptune makes a delicate 3 to 4 resonance that should have been shattered eons ago by passing stars, galactic tides, or the gravitational jostling of other giant planets. Imagine a marble rolling around a giant bowl influenced by a magnet held just outside the rim. Normally, the marble would lose sync quickly, but Varuna's orbit clings to this alignment with eerie precision. Some researchers argue this could be a frozen relic from the solar system's infancy, a time when Neptune's migration through the outer solar system sent shockwaves through the Kuiper Belt, ensnaring objects like Varuna in temporary gravitational traps. But there's a darker possibility. Varuna might not be alone in this resonance. Hidden siblings, objects too faint or distant for our telescopes to spot, could share similar orbits, their collective gravity reinforcing the pattern like invisible anchors. This would mean Varuna isn't an outlier but part of a hidden network of worlds bound by Neptune's influence, a secret society of icy bodies whispering to one another across the void. The resonance also hints at violence. For Varuna to settle into this rhythm, something must have drastically altered its original path, perhaps a close encounter with Neptune itself or a cataclysmic collision that ejected it from a more conventional orbit. Picture a pinball ricocheting off bumpers until it finally lands in just the right groove, except here the bumpers are planetary giants, and the game has been playing out for billions of years. Yet the biggest mystery isn't how Varuna got here, it's why the resonance persists. Most gravitational locks in the Kuiper Belt dissolve over time, worn down by countless tiny perturbations. Varuna's stubborn adherence to the pattern suggests unseen forces might be at work, whether from undiscovered masses subtly tugging at it or complexities in Neptune's own gravitational field we don't yet understand. Every calculation leaves room for doubt, as if the universe itself is teasing us with a puzzle just beyond our grasp. This isn't just about orbits, it's about time. If Varuna's resonance is a fossil from the solar system's birth, it could help us reconstruct the chaotic era when planets roamed like nomads, scattering smaller worlds in their wake. But if the resonance is actively maintained by something we can't see, it forces us to reconsider what might still be lurking in the darkness, orchestrating the motions of these distant icy wanderers. Either way, Varuna's path isn't just a curiosity, it's a trail of breadcrumbs leading back to the solar system's most turbulent secrets. Varuna's density shouldn't be this controversial, yet it sparked a debate that cuts to the very core of what this distant world might be made of. Some measurements suggest a lightweight, porous structure, like a cosmic sponge held together by feeble gravity. Others paint a starkly different picture, a bizarrely dense object packed tighter than any typical Kuiper Belt resident. How can one small world defy classification so completely? The answer might rewrite our understanding of how objects form in the solar system's frozen fringes. Let's start with the fluffy Varuna theory. If its density leans toward the lower estimates, this implies a rubble pile interior, a loose collection of ice and rock barely clinging together, with gaps and voids making up nearly half its volume. Picture a snowball smashed and hastily reassembled, full of empty spaces where fragments didn't quite fit back together. This would align with its rapid spin. A fragile structure could stretch under the strain, explaining its elongated shape without flying apart. But here's the catch: most rubble piles in the Kuiper Belt don't spin this fast without disintegrating. So if Varuna's porous, what unseen force is binding it together against the odds? Now flip the script to the high-density scenario. If Varuna's unexpectedly compact, it could mean one of two shocking things. Either it's loaded with heavier elements like silicates or metals, materials rarely found this far out, or it hides vast pockets of hyper-compressed ice beneath its surface. Imagine an ice giant's core, forged under pressures so intense that molecules lock into exotic crystalline forms, squeezing into spaces they'd never occupy naturally. This would make Varuna less of a snowball and more of a cosmic iceberg, its true mass lurking unseen beneath a deceptive outer shell. Then there's the wild card, a subsurface ocean, frozen solid or otherwise. Water, when mixed with ammonia or salts, can remain liquid at brutally low temperatures. If Varuna once hosted such a layer, its slow freeze over eons could have created dense, high-pressure ice phases like Ice 6 or Ice 7. Structures so alien they behave more like rock than the ice we know. This would explain conflicting density readings, a squishy outer layer masking a rigid, almost metallic heart, but the plot thickens when we compare Varuna to its neighbors. Most Kuiper Belt objects cluster around predictable density ranges, making this outlier's contradictions even more jarring. Could it be an interloper born closer to the Sun before being hurled outward during the solar system's chaotic youth? Or does its strange density hint at a catastrophic collision that remixed its interior, leaving behind a hybrid of shattered debris and crushed remnants? The most unsettling possibility: we're misreading the data entirely. Varuna's dark surface complicates measurements, and its odd shape distorts mass calculations. What if the density debate isn't about Varuna's composition at all, but our own incomplete grasp of how to study such distant, enigmatic worlds? Until a spacecraft finally visits, this puzzle remains a stark reminder. Even in the age of precision astronomy, the outer solar system still holds secrets that defy our best tools and theories. The absence of moons around Varuna isn't just unusual, it's a statistical anomaly that borders on defiance. Nearly half of all known Kuiper Belt objects its size or larger travel with at least one satellite in tow, from Pluto's entourage of 5 to Haumea's pair of icy companions. Yet despite exhaustive searches, Varuna orbits in solitary silence, a stark outlier in a cosmic neighborhood where celestial companionship is the norm. This lonely state raises a haunting question: is Varuna truly alone, or are we missing something fundamental about this distant world? One compelling explanation points to violence specifically, a catastrophic impact powerful enough to strip away any moons it once possessed. Picture a younger Varuna, perhaps circled by several small satellites, until a colossal collision sent shockwaves through its gravitational grasp. The force could have shattered orbiting bodies into dust or sent them careening into the abyss, like a wrecking ball scattering marbles across a frozen pond. Supporting this theory is Varuna's bizarre shape and dizzying spin, both potential fingerprints of a primordial smash-up. If true, the same event that warped its body might have purged its skies, leaving behind a solitary survivor spinning wildly through the void. But impacts aren't the only way to lose a moon. Gravitational theft could also explain their absence. Neptune's immense pull has reshaped the Kuiper Belt over billions of years, potentially plucking satellites from objects like Varuna and either consuming them or flinging them deeper into space. Imagine a cosmic game of tug-of-war where the giant planet's gravity slowly overpowered Varuna's hold, leaving it moonless. This scenario gains traction when we consider Varuna's peculiar orbital resonance with Neptune, a relationship that might have come at the cost of its celestial companions. Then there's the observational blind spot. Our current tools might simply be missing what's there. Varuna's distance and dark surface make spotting faint, close-orbiting moons nearly impossible with today's technology. A small satellite could be hiding in its glare, much like Pluto's tiniest moons remained undetected until New Horizons flew past. Or perhaps any moons are made of the same ultra-dark material as Varuna itself, rendering them virtually invisible against the blackness of space. Even Earth's most powerful telescopes have limits, and the Kuiper Belt specializes in humbling our confidence. The most unsettling possibility: Varuna never had moons to begin with. While most large Kuiper Belt objects form with debris disks that coalesce into satellites, some rare outliers might emerge from chaotic collisions that leave no orbiting material behind. This would make Varuna a cosmic oddity from birth, a world forged in a unique event that skipped the usual moon-forming steps. If true, its existence challenges our models of how these distant icy bodies evolve, hinting at formation pathways we've yet to fully imagine. Yet the mystery deepens when we consider timing. If collisions or theft explain the missing moons, why haven't new ones formed from debris over billions of years? Other impact survivors in the Kuiper Belt eventually require satellites, yet Varuna persists in its solitude. This suggests either an exceptionally clean environment with no spare material to form new companions, or some ongoing mechanism that prevents moons from taking hold, like its extreme spin destabilizing potential orbits. What makes this enigma so crucial is what it reveals about the outer solar system's hidden dynamics. Moons aren't just decorative, they're time capsules preserving information about their host world's mass, history, and even internal structure. Their absence around Varuna leaves us groping in the dark, forced to reconstruct its past through indirect clues and contradictory evidence. Until we send a probe to this lonely wanderer or develop telescopes capable of spotting its hypothetical hidden companions, its missing moons will remain one of the most stubborn puzzles in the Kuiper Belt, a silent testament to how much we still have left to learn about the solar system's frozen frontier. Varuna isn't just a static, unchanging relic. It's a world that seems to breathe, shifting hues in ways that baffle astronomers. Over the years, telescopic observations have caught subtle but unmistakable variations in its color, flickering between a deep, reddish-black and a slightly lighter, almost rusty tint. These shifts aren't random noise in the data. They follow a loose, cyclical pattern, like a cosmic mood ring reacting to forces we can't yet see. What could possibly cause such transformations on a world so far from the sun's warmth, where temperatures hover near absolute zero? One leading suspect is solar radiation. Not the gentle sunlight we know, but the brutal onslaught of ultraviolet and cosmic rays that batter Varuna's surface relentlessly. These high-energy particles can break apart simple molecules in the ice, triggering chemical reactions that produce new, darker compounds. Picture a loaf of bread left in the oven too long. The surface gradually darkens as heat rearranges its chemistry. On Varuna, this process might unfold in slow motion, with radiation toasting patches of its surface over decades or centuries, creating temporary stains that fade as fresh ice is exposed. But there's a twist. These color changes don't always correlate with Varuna's distance from the sun, ruling out simple solar heating as the sole culprit. Instead, some researchers point to seasonal shifts, except here, seasons last centuries, not months. Varuna's tilt and elliptical orbit could expose different hemispheres to varying levels of radiation over millennia, creating slow-motion waves of chemical alteration. Imagine a glacier on Earth that darkens in summer and brightens in winter, but stretched across time frames longer than human history. Then there's the wild card, cryovolcanism. If Varuna's surface is occasionally repaved by eruptions of fresh ice, these events could reset its color like a cosmic etch-a-sketch. Bright, newly exposed patches would gradually darken under radiation, only to be buried again by the next eruption, creating cyclical shifts in overall hue. The challenge: we've never directly observed such activity this far out in the solar system, leaving us to piece together clues from distant spectra and flickering brightness readings. The most tantalizing possibility involves something far stranger. Varuna's rotation might be uneven, wobbling like a spinning top running out of steam. This could cause its darker and lighter regions to face Earth at different angles over time, creating the illusion of color changes when in reality, we're just seeing different sides of a mottled surface. If true, this wobble could hint at an unevenly distributed interior, with dense pockets of material tugging the world slightly off balance as it spins. Yet the biggest mystery isn't the how, it's the why now. Color variations in Kuiper Belt objects are rare, and when they do occur, they're usually tied to obvious events like collisions or extreme solar activity. Varuna's shifts, however, seem almost rhythmic, as if guided by an internal clock we don't yet understand. Could there be underground reservoirs of volatile chemicals slowly seeping to the surface? Or does its dark, porous crust trap and release sunlight in unpredictable ways, like a celestial sponge squeezing out stains? Every hypothesis raises more questions than answers, turning Varuna's color changes into a cosmic Rorschach test, one where each observer sees a different pattern, but no one yet holds the key to the full picture. Until we witness these shifts up close, they'll remain one of the most poetic mysteries in the outer solar system, a world that doesn't just sit silently in the dark, but whispers its secrets in shades of red and black, waiting for us to decipher its language. Varuna's reflectivity tells a story written in contradictions, a tale where light and shadow dance to rhythms that defy explanation. While most celestial objects brighten and dim in perfect sync with their rotation, Varuna's albedo flickers unpredictably, as if its surface can't decide how much sunlight to throw back into the void. These irregularities aren't mere measurement errors, they're clues to something far more profound happening on or beneath this distant world's icy crust. One striking anomaly: Varuna's brightness shifts don't align with its 6-hour spin. If surface variations alone were responsible, we'd expect a regular pattern, darker and lighter regions rotating into view like clockwork. Instead, the changes seem almost capricious, with reflectivity spikes appearing at random intervals, sometimes lingering longer than a full rotation should allow. This suggests the surface isn't uniformly static. It's alive with processes that alter its reflective properties on the fly. A leading hypothesis points to volatile ices sublimating directly from solid to gas in fleeting bursts. Imagine dry ice vanishing from a laboratory table, but on a planetary scale. Methane or nitrogen patches could be vaporizing under rare alignments of sunlight, temporarily exposing brighter underlying ice before new dark material drifts back over the area like a cosmic veil. This would create localized bright spots that appear, vanish, and reappear out of phase with Varuna's rotation, a phenomenon observed nowhere else in the Kuiper Belt with such intensity. Then there's the puzzle of wind. Yes, wind on a world with virtually no atmosphere. Some models suggest that even Varuna's tenuous exosphere might allow micron-thin layers of dark dust to shift across its surface, blown by sublimating gases at speeds of just centimeters per year. Over decades, these slow-motion sandstorms could redistribute material, brightening some areas while staining others like shadows creeping across a floor at glacial speed. The most tantalizing theory involves cryovolcanic plumes. If geysers occasionally erupt from Varuna's interior, they could coat surrounding terrain with fresh frost before radiation darkens it again. Picture Old Faithful erupting in Yellowstone, but instead of water, imagine crystal-clear ammonia ice particles snowing back down, creating temporary reflective blankets that disrupt the usual albedo patterns. These eruptions wouldn't need to be frequent, just often enough to throw off long-term observations. Yet the real enigma lies in the timescales. Some reflectivity changes unfold over weeks while others persist for years, implying multiple overlapping processes. Could there be seasonal cycles at work, where temperature variations too subtle for us to measure trigger chemical changes in surface ices? Or does Varuna's dark crust act like a sponge, absorbing and releasing microscopic volatile particles in response to cosmic ray bombardment? The implications stretch beyond Varuna itself. If such dynamic albedo variations are possible this far from the Sun, how many other distant worlds might be hiding similar activity? We've long assumed Kuiper Belt objects to be inert time capsules, but Varuna's shimmering inconsistencies suggest they might be far more mercurial, their surfaces rewriting themselves in ways we're only beginning to decode. Every flicker of light from this tiny world is a reminder, even in the frozen depths of space, change is the only constant. In the vast orchestra of the cosmos, most celestial bodies hum with electromagnetic whispers, subtle radio waves generated by charged particles, magnetic fields, or even the faint scrape of solar wind across their surfaces. Yet Varuna stands apart, a cosmic mute in a universe thrumming with static. Despite sharing size and composition with other Kuiper Belt objects that crackle with detectable radio emissions, this distant world remains stubbornly silent, its radio signature barely rising above the background noise of space. What could explain such eerie quiet from an object that, by all rights, should be singing along with its neighbors? One possible culprit lies in Varuna's peculiar composition. Many icy bodies emit radio waves when solar radiation excites molecules on their surfaces, creating fleeting charges that ripple outward like ripples in a pond. But if Varuna's crust is dominated by unusually thick, insulating layers of dark organic sludge, those same carbon-rich compounds that paint its surface black, this material could act like an electromagnetic sponge, absorbing or scattering radio frequencies before they escape into space. Picture shouting into a room lined with soundproofing foam. No matter how loud you are, almost nothing escapes the walls. Varuna's murky outer layers might be doing the same thing, but with radio waves instead of sound. Then there's the magnetic field, or rather, the glaring lack of one. Planets like Earth and Jupiter generate powerful radio emissions through the churn of molten metal in their cores, creating dynamos that broadcast their presence across the solar system. Even smaller icy worlds often retain traces of ancient magnetism or temporary fields induced by solar wind. Yet if Varuna's interior is as cold and geologically dead as some models suggest, a frozen relic with no conductive fluid circulating beneath its shell, there'd be no engine to power radio transmissions. It would be less like a radio tower and more like a stone, silent, passive, and electromagnetically inert. But the plot thickens when we consider alternative explanations. Some researchers speculate that Varuna's rapid rotation could be scrambling any potential radio emissions, dispersing them across frequencies too broad for our instruments to detect clearly. Imagine tuning a radio dial while spinning it wildly. The signal fractures into fragments, becoming indistinguishable from static. If Varuna's whirligig spin stretches its emissions thin across the spectrum, what might appear as silence could actually be a smeared-out signal we simply haven't learned to decode. The most intriguing possibility, though, involves Varuna's past. Radio emissions often depend on interactions with the solar wind, but if this world was born farther out in the Kuiper Belt, where the Sun's influence is weaker, it might have missed the charging phase that taught other objects to broadcast. Alternatively, a cataclysmic collision could have stripped away volatile ices that normally generate radio noise, leaving behind a dense, radio-dead core cloaked in electrically inert debris. Yet the real puzzle isn't just Varuna's silence, it's the inconsistency. Other similarly distant, dark, and icy objects somehow manage to whisper across the radio spectrum, even if faintly. This leaves scientists wrestling with a haunting question. Is Varuna's hush a quirk of its unique history and structure, or are we fundamentally misunderstanding how radio emissions work in the outer solar system? Every theory leads back to the same chilling realization sometimes: what a world doesn't say speaks volumes. Varuna doesn't spin like a top, it rolls like a bowling ball dropped onto a tilted lane. While most Kuiper Belt objects rotate with their axes roughly perpendicular to their orbital planes, Varuna's poles point almost sideways, leaving it spinning nearly parallel to its path around the Sun. This extreme axial tilt, known as obliquity, shouldn't exist in such a cold, distant world, yet there it is, defying expectations with every rotation. How could a relatively small, icy body end up in such a bizarre orientation? And what does this tell us about the violent history of the outer solar system? One of the most plausible explanations points to a colossal impact, a collision so catastrophic it literally knocked Varuna onto its side. Picture a cue ball slamming into a billiard ball at a sharp angle, sending it spinning in a new direction. If a massive object plowed into Varuna billions of years ago, the force could have torqued its rotation axis dramatically, leaving it frozen in this lopsided state ever since. This theory gains traction when we consider Varuna's elongated shape and rapid spin, both potential hallmarks of a violent encounter that reshaped the world inside and out. The collision might have been so forceful that it ejected enough material to form temporary moons, which later escaped or fell back onto the surface, leaving no trace of the cataclysm except this lingering tilt. But impacts aren't the only way to tilt a world. Gravitational nudges from Neptune could have played a role, especially during the solar system's chaotic infancy. As Neptune migrated outward, its gravity may have perturbed nearby objects, gradually tugging them into new rotational alignments through a process called quasi-resonance. Imagine a spinning gyroscope slowly wobbling off axis as an invisible hand nudges it over millennia. If Varuna was caught in this gravitational dance, its axis might have been methodically tipped over time, not by a single violent event, but by the patient, relentless influence of a giant planet's pull. This would explain why its tilt is so extreme compared to neighboring Kuiper Belt objects that avoided Neptune's gravitational grip. Yet the weirdest possibility involves Varuna's internal structure. If its core is denser on one side, perhaps from uneven freezing of a subsurface ocean or the accumulation of heavy elements after an ancient collision, this imbalance could have caused its rotation axis to gradually migrate over eons. Think of a tire with a weight strapped to one side. As it spins, the uneven distribution forces it to wobble. On a planetary scale, this process could have reoriented Varuna's poles without any outside interference, turning it into the cosmic oddball we see today. The implications stretch beyond mere curiosity. Axial tilt dictates seasons, climate, and even geological activity, yet Varuna's extreme case challenges our understanding of how these forces operate in the outer solar system. Without the sun's warmth to drive seasonal changes, what does obliquity mean for a world like this? Could it expose certain regions to more cosmic radiation, or influence how volatile ices migrate across its surface over astronomical timescales? Perhaps most tantalizing of all, Varuna's tilt might be a clue to something larger. If other undiscovered Kuiper Belt objects share similar obliquities, they could form a hidden population sculpted by the same ancient upheaval, whether a rogue planetary encounter, a shared gravitational disturbance, or a forgotten chapter in Neptune's migration. Each possibility peels back another layer of the solar system's untold history, written in the silent language of celestial mechanics. Until we uncover more of these tilted worlds, Varuna's crooked spin remains a solitary enigma, a cryptic hint that the outer darkness still holds stories we've only begun to read. Varuna's surface chemistry reads like a cosmic crime scene, one where key ingredients have mysteriously vanished without a trace. While most large Kuiper Belt objects wear frosty coats of volatile ices like methane or nitrogen, Varuna's spectral fingerprints show a glaring absence, as if someone scrubbed away the very compounds we'd expect to find in abundance. This isn't just a minor discrepancy, it's a fundamental anomaly that forces us to reconsider where and how this distant world formed. The simplest explanation: escape. Volatiles are notoriously flighty, prone to vaporizing into space when temperatures rise even slightly. If Varuna once had methane or nitrogen veneers, a past close approach to the sun, or internal heating from radioactive decay could have stripped them away over billions of years. Picture an ice cube left on a summer sidewalk, shrinking hour by hour until only a dark stain remains. On a planetary scale, this process might have left Varuna's surface barren. Its once glittering ices boiled off into the void, leaving behind only the tougher, darker residues we see today. Yet this theory hits a snag when we compare Varuna to similar objects. Pluto's surface, despite being smaller and closer to the Sun, still clings to vast plains of nitrogen ice. Even more distant bodies like Makemake show methane deposits, defying expectations that volatiles should have fled long ago. This raises an unsettling question. Why would Varuna lose its volatiles when others under comparable or harsher conditions held onto theirs? Some researchers argue that Varuna's rapid spin might have flung escaping molecules into space more efficiently, like a spinning wet towel shedding droplets. Others speculate its dark, heat-absorbing surface could have accelerated the loss, creating a feedback loop where darker patches grew hotter, vaporizing more ices, which made the surface darker still, a runaway process until only the dregs remained. The alternative is even more provocative. What if Varuna never had significant volatiles to begin with? This would imply it formed in a different region of the primordial solar system, one starved of the nitrogen and methane that enriched its cousins. Imagine two siblings raised in separate homes, one in a mansion stocked with fine foods, the other in a sparse cabin with only the hardiest staples. Varuna might hail from the cosmic equivalent of that cabin, born in a chemically impoverished zone where lightweight molecules were scarce. Supporting this idea are recent models suggesting the outer solar system wasn't uniformly mixed. Some patches could have been dominated by heavier organics, while others collected the fluffy, volatile, rich ices we associate with Kuiper Belt objects. This opens a darker possibility. Varuna might be an immigrant if it didn't form in the Kuiper Belt at all, but was instead flung outward during the solar system's chaotic youth. Its odd composition would make perfect sense. A birthplace closer to the giant planets where temperatures were too high for volatiles to condense could explain its missing methane and nitrogen, branding it as an outsider in its current neighborhood. The scars of that ancient migration might still be visible in its peculiar orbit and spin, hinting at a violent past we're only beginning to unravel. But the plot thickens when we consider the exceptions. Faint spectral signatures suggest traces of water ice, a stubborn outlier that refuses to fit the narrative. If volatiles escaped or were never present, why does water, a molecule just as prone to sublimation, persist? Some scientists propose that water's stronger molecular bonds allow it to survive where flimsier ices fail, clinging to cracks and shadows like cosmic moss. Others wonder if Varuna's water isn't surface frost at all, but part of a deeper, ancient layer occasionally exposed by impacts or cryovolcanism, creating fleeting glimpses of a wetter past. The missing volatiles aren't just a chemical curiosity, they're a time capsule. Every molecule lost or retained holds clues about Varuna's journey through billions of years of solar system history. Did it wander closer to the Sun in its youth, baking away its icy veneer? Was it born in a cosmic backwater where the building blocks of life were scarce? Or does its barren surface hide underground reservoirs, locked away beneath layers of carbon-rich armor? Until we peer closer, these absences will loom as large as any presence, whispering secrets we're not yet equipped to hear. Varuna's light curve doesn't just flicker, it stumbles, lurching through brightness changes like a candle flame fighting a gusty wind. Unlike most rotating objects, which dim and brighten with clockwork regularity as their surfaces turn toward and away from us, Varuna's luminosity dances to a far more chaotic rhythm. Some peaks arrive too early, others linger too long, and a few vanish entirely before reappearing cycles later. This isn't just observational noise, it's a glaring sign that something deeply unusual is happening on or within this distant world, something that refuses to play by the rules. The leading suspect, Varuna's bizarre, lopsided shape. A perfectly symmetrical object would present the same profile with each rotation, creating smooth, predictable brightness variations. But if Varuna is more like a cosmic potato bulging on one side, flattened on another, or even sporting irregular surface features like massive craters or ridges, its light curve would skew unpredictably. Imagine spinning a lumpy clay pot under a lamp. The shadows it casts would shift erratically, not in a clean, repeating pattern. For Varuna, this could mean that as it twirls, different facets of its jagged form catch and reflect sunlight in ways that baffle our models, leaving astronomers scratching their heads at each new observation. Yet shape alone might not tell the full story. Some researchers point to active surface processes, landslides of dark carbon-rich material, perhaps, or fresh ice exposures from tiny cryovolcanic eruptions. Picture a mountainside on Earth collapsing after a rainstorm, sending tons of debris sliding into a valley below. On Varuna, similar events could occur in slow motion over centuries, with patches of darker regolith slipping to reveal brighter layers underneath. These sudden changes would abruptly alter how much light the surface reflects, introducing random spikes or dips in the light curve that no rotation model could anticipate. Then there's the wild card, internal dynamics. If Varuna's core isn't uniformly dense, if pockets of slushy ice or even liquid brine shift beneath its crust, these imbalances could cause the entire world to wobble as it spins. Think of a washing machine with an uneven load, thumping erratically instead of humming smoothly. Such a wobble would make Varuna's rotation subtly unstable, presenting slightly different surface geometries to Earth-bound observers with each cycle. Over time, these tiny variations would snowball into a light curve that looks less like a sine wave and more like a seismograph during an earthquake. The implications stretch far beyond Varuna. If this kind of irregular activity is possible in the frozen depths of the Kuiper Belt, it forces us to reconsider how dead these distant worlds truly are. We've long assumed objects this far from the Sun would be static, frozen in time. But Varuna's flickering suggests otherwise, whether through shifting surface ices, hidden internal movements, or a structure so misshapen it defies simple explanation. This tiny world proves that even in the darkest corners of the solar system, change is the only constant. And perhaps most unsettling of all, we might be seeing just the tip of the iceberg. Current telescopes can only resolve Varuna as a faint pixel, leaving its true nature cloaked in shadow. What looks like a smooth brightness change from Earth could be the blended signature of a dozen smaller, more chaotic events playing out across its surface. Until a spacecraft visits this distant enigma, every flicker of its light will remain an open question, a coded message from the edge of the known solar system, waiting for someone to crack its cipher. Varuna's infrared fingerprint is a cosmic paradox, an unmistakable pattern that shouldn't exist. When astronomers split its faint light into a spectrum, they don't see the familiar chemical signatures of methane or nitrogen ices common to most Kuiper Belt objects. Instead, the data reveals jagged, unfamiliar absorption lines, as if some unknown substance is absorbing specific wavelengths of light and leaving behind a spectral graffiti no one can fully decipher. This isn't just a minor deviation, it's a glaring red flag that Varuna's surface harbors materials we've never catalogued in the outer solar system. One possible explanation lies in irradiated organic sludge. When simple carbon compounds like methane are bombarded by cosmic rays over billions of years, they can polymerize into complex, tar-like substances called tholins. These macromolecules are notorious for their dark, reddish hue and their ability to warp light in unpredictable ways. Picture asphalt baking under a desert sun, slowly cracking and reforming into new chemical configurations. On Varuna's surface, a similar process might have transformed primordial ices into a thick, photochemically altered crust, one so chemically convoluted that it defies easy classification. But tholins alone can't explain the full spectrum. Some absorption bands suggest the presence of exotic hydrated minerals, possibly forged in ancient underground oceans that have long since frozen solid. On Earth, minerals like gypsum or epsomite form when water interacts with certain rocks. If Varuna once hosted liquid water beneath its crust, similar interactions could have left behind spectral scars visible only in infrared. Imagine a frozen brine percolating through rocky veins, depositing crystalline oddities as it went, then locking them away in a deep freeze for eternity. The real curveball, a few spectral lines hint at silicon compounds, materials more commonly associated with asteroids than icy worlds. If confirmed, this would imply Varuna either formed in a region rich in silicates far closer to the Sun than its current home, or suffered a catastrophic collision that dredged up deep, rocky material from its core. Either scenario rewrites the origin story of this distant world, painting it as less of a pristine ice ball and more of a hybrid misfit, stitched together from mismatched solar system leftovers. Then there's the tantalizing possibility of something entirely new. Just as quantum physics introduced elements that defied the periodic table's neat order, Varuna's spectrum might be whispering the existence of minerals or ices stable only under extreme cold and pressure substances with no earthly counterparts. Lab experiments have predicted bizarre forms of ammonia water crystals or methane clathrates that could form in the Kuiper Belt's frigid environment, but none perfectly match Varuna's data. It's like hearing a musical chord where none of the notes align with any known instrument. The implications ripple outward. If Varuna's spectral anomalies stem from unique formation conditions, it could represent an entire class of dark hybrids lurking in the Kuiper Belt worlds that straddle the line between comet, asteroid, and something else entirely. Alternatively, if the culprit is space weathering, we've underestimated how profoundly radiation can alter surface chemistry over billions of years. Either way, this tiny world's light carries a message we're only beginning to decode. The outer solar system's ingredient list is far stranger and far richer than we ever imagined. Varuna's surface doesn't just defy expectations, it taunts them. While most Kuiper Belt objects wear their age with pride, covered in the pockmarks of ancient impacts, Varuna presents an unsettlingly smooth visage, like a frosted pane of glass untouched by time. This cosmic anomaly raises an immediate red flag. In a neighborhood where collisions have been the norm for billions of years, how has this particular world managed to avoid the scars that mark its neighbors? The answer might rewrite our understanding of geology in the solar system's frozen outback. Take Pluto as a perfect counterexample. Its surface resembles a celestial battlefield, with sprawling impact basins like Sputnik Planitia testifying to a violent past. Even smaller Kuiper Belt objects like Haumea and Quaoar show craters galore. But Varuna scans reveal what appears to be a curiously unblemished surface, with only faint hints of topographical variation. This isn't just unusual, it's statistically improbable, like finding a pristine sand dune in the middle of a meteorite testing range. One radical explanation points to active resurfacing, a process where fresh material bubbles up from below to erase old scars. On icy moons like Europa and Enceladus, this happens through cryovolcanism or tectonic activity powered by tidal heating. Varuna has no nearby giant planet to flex its interior, but residual heat from radioactive decay or the slow freezing of a subsurface ocean could provide just enough energy to smooth its face over time. Imagine squeezing a tube of toothpaste in slow motion over eons. Even sluggish geological processes could repaint Varuna's surface, hiding ancient wounds under fresh coats of ice. Then there's the marshmallow theory, the possibility that Varuna's crust is so soft and porous that impacts simply don't leave lasting marks. When a meteorite strikes a fluffy snowbank, it creates only a temporary dent before the snow collapses back into shape. If Varuna's near-surface layers consist of loosely packed ice grains or organic sludge, incoming space rocks might sink in without forming proper craters, like stones dropped into thick mud. This would make Varuna less of a rigid world and more of a cosmic stress ball, absorbing violence without showing the bruises, but the most unsettling possibility. Our eyes might be deceiving us. Current telescopes can only resolve Varuna as a handful of pixels, meaning what appears smooth could actually be a rough surface obscured by its own darkness. Picture trying to judge the texture of a black velvet painting from across a football field. Details vanish in the murk. Until we get a probe close enough to image Varuna directly, we can't rule out that its craters are simply too subtle for our instruments to detect against its light-absorbing surface. The implications ripple outward. If Varuna is actively resurfacing, it joins an elite club of geologically active worlds, one we never expected to include such distant, frozen bodies. If its crust is uniquely soft, we must rethink how materials behave in the outer solar system's extreme cold, and if it's all an observational illusion. That itself reveals how little we truly know about the textures of these faraway realms. Varuna's smoothness isn't just a curiosity, it's a mirror reflecting the limits of our knowledge, showing us how much remains hidden in the darkness. Varuna's thermal map reads like a cosmic fever dream, pockets of unexpected warmth scattered across its frozen surface like embers refusing to die in a snowstorm. For a world so distant that sunlight is barely more than a faint whisper, these thermal anomalies make no sense. Standard models predict a uniformly frigid landscape, yet Varuna's reality is anything but uniform. Some regions hover just a few degrees above the surrounding chill, while others spike dramatically, as if the ground itself is generating heat. What could possibly be cooking beneath this icy shell? One tantalizing explanation points to subsurface friction, layers of ice grinding against each other as Varuna spins at breakneck speed. Imagine squeezing a rubber ball repeatedly in your hand until it warms from the motion alone. Only here the forces are planetary in scale. If Varuna's interior isn't perfectly rigid, its rapid rotation could generate enough internal movement to create localized hotspots, like a celestial version of rubbing your hands together for warmth in the dead of winter. Then there's the possibility of radioactive decay. While Varuna isn't massive enough to retain primordial heat like Earth, certain radioactive isotopes trapped in its core could still be decaying, releasing energy in slow, steady pulses. Picture a lump of uranium buried deep in Antarctica, quietly radiating heat for millennia, except Varuna's version might be laced with thorium or potassium, leftovers from the solar system's violent birth. But the real curveball, insulation. Varuna's dark, porous surface might act like a thermal blanket, trapping heat beneath layers of carbon-rich sludge. Think of how a black asphalt road absorbs sunlight during the day and stays warm long after sunset. Now scale that up to a planetary body where pockets of warmth persist in shadowed cracks and crevices, defying the icy vacuum around them. The wildest theory, though, involves chemistry. Certain mixtures of ice and ammonia can lower the freezing point of water dramatically, creating briny slush that remains semi-liquid even in extreme cold. If Varuna's subsurface contains these antifreeze-like compounds, they could generate heat through exothermic reactions as they shift states, like invisible underground furnaces flickering to life. Yet the most perplexing detail isn't just the heat, it's the pattern. These warm zones don't follow predictable distributions based on sunlight exposure or surface composition. Some cluster near the equator, while others dot the poles haphazardly, as if guided by unseen plumbing beneath the crust. Could there be underground reservoirs channeling warmth like geothermal vents, or fractures venting heat from depths we can't yet probe? Every explanation raises new questions. If friction or radioactivity were at play, why don't other Kuiper Belt objects show similar anomalies? If chemistry is the key, what stopped these reactions from playing out billions of years ago? And if Varuna truly harbors subsurface activity, how many other distant worlds might be hiding similar secrets? Until a spacecraft finally visits this icy enigma, these temperature fluctuations remain more than just scientific curiosities. They're breadcrumbs leading us toward a deeper truth about the dynamism of the outer solar system's forgotten realms. Varuna's gravity doesn't behave like it should. It tugs and resists in ways that defy the neat equations we use to predict celestial motion. When astronomers track its influence on nearby objects or analyze subtle perturbations in its orbit, the numbers refuse to add up cleanly. Instead, they reveal a gravitational fingerprint riddled with inconsistencies, as if something hidden beneath its icy shell is warping the very fabric of its pull. These anomalies aren't random noise, they're clues pointing to an interior far stranger than the frozen ball we see from afar. One compelling possibility. Varuna's core isn't uniform. Most small bodies in the Kuiper Belt distribute their mass evenly, like a scoop of ice cream left to melt into a smooth puddle. But Varuna's gravity hints at pockets of unexpected density regions where mass clumps together or vanishes entirely, creating a lopsided gravitational landscape. Imagine a chocolate chip cookie where the chips aren't sprinkled but buried in uneven handfuls. Bite into one spot, and you hit a dense cluster, another, and you find only crumbs. If Varuna's interior mirrors this patchwork, it could explain why its gravity fluctuates in ways that baffle our models. But what could create such irregularity? The answer might lie in violence. A catastrophic collision billions of years ago could have shattered Varuna's original structure, scattering dense core fragments amid lighter debris before gravity reassembled them into a haphazard, unstable jumble. Picture a snow globe smashed against a wall. The water and glitter inside don't settle evenly, but pool in chaotic, uneven patches. If Varuna's formation involved a similar smash and grab scenario, the scars of that chaos could still linger beneath its surface, frozen in time. Then there's the void theory. Some gravitational fluctuations suggest hollow spaces lurking beneath Varuna's crust, vast caverns carved by ancient cryovolcanic activity or the slow sublimation of volatile ices. On Earth, we see similar, if smaller, effects in lava tubes or underground caves, where missing mass creates subtle gravitational dips. Scale that up to a planetary body, and you have a Swiss cheese interior riddled with tunnels and chambers that distort its pull. If true, this would make Varuna less a solid world and more a fragile shell, its hidden emptiness echoing with the ghosts of long-lost eruptions or escaping gases. The wildest hypothesis, Varuna might be hiding a captive relic from its birth. Gravitational math hints at the possibility of a dense, rocky chunk trapped near its core, a fossilized piece of the primordial solar system that never fully blended into the surrounding ice. This intruder could be a remnant of the violent era when planets formed, a wandering planetesimal that collided with Varuna and sank to its heart like a stone dropped into pudding. If confirmed, it would mean this distant world isn't just an icy remnant, it's a cosmic museum, preserving a piece of solar system history in its gravitational grip. Yet the most unsettling part isn't the anomalies themselves, it's their persistence. Over time, gravity should smooth out irregularities, redistributing mass until equilibrium is reached. The fact that Varuna's imbalances endure suggests active forces resisting this balance, perhaps residual heat stirring its interior, or a spin so rapid it counteracts the calming pull of gravity. Either way, this tiny world refuses to conform, its gravitational quirks standing as silent testimony to processes we've yet to understand. What makes these mysteries so vital is their echo across the cosmos. If Varuna's uneven gravity stems from a violent past, how many other Kuiper Belt objects share similar hidden scars? If voids or captive relics shape its pull, what does that say about the diversity of worlds lurking in the dark? Every irregularity in Varuna's gravitational field isn't just a puzzle, it's a window into the turbulent, unfinished story of our solar system's farthest reaches. Until we send a probe to study its whispers up close, these gravitational ghosts will keep tugging at our curiosity, refusing to let go. Varuna's silence extends beyond radio waves. It's missing something even more fundamental, a dust halo. Nearly all rapidly spinning celestial bodies, from asteroids to dwarf planets, shed material into space, creating faint but detectable rings or clouds of debris. These dusty signatures act like cosmic breadcrumbs, revealing a world's composition and history. Yet Varuna, despite its dizzying rotation speed, shows no trace of such a halo. This absence isn't just odd, it's a direct challenge to our understanding of how objects behave in the outer solar system. One explanation could be Varuna's unusual strength. Most fast-spinning objects fling dust outward because centrifugal force overcomes their weak gravity. But if Varuna's interior is denser or more cohesive than typical Kuiper Belt objects, perhaps packed with tightly bound rubble or sintered ice, its gravity might be strong enough to hold onto loose particles despite the spin. Imagine a child spinning on a merry-go-round while clutching a bag of marbles. If their grip is strong enough, nothing spills, even at high speeds. Varuna's gravitational grip could be similarly tenacious, preventing the steady escape of material that would form a halo. Then there's the environmental factor. The outer solar system isn't just cold, it's practically sterile, with far fewer micrometeorites buzzing around compared to the asteroid belt. These tiny impacts are crucial for dust production, chipping away at surfaces and kicking up debris. If Varuna orbits through a relatively empty neighborhood, it might experience fewer collisions that would normally replenish a dust cloud. Picture a lone rock in a vast desert, weathering so slowly that no sand accumulates around it. Without constant bombardment, even a fragile world could appear unnaturally clean. But the most intriguing possibility involves Varuna's dark, sticky surface. Spectral data suggests its crust might be laced with complex organic compounds, tar-like substances that could act like cosmic glue. When dust is created, whether through impacts or thermal fracturing, these compounds might immediately trap it back onto the surface. On Earth, we see similar behavior in wet sand versus dry. One clumps together while the other scatters easily. If Varuna's exterior is more wet sand than dry, any liberated particles would quickly reattach, starving a potential halo before it could form. The implications reach far beyond one oddball world. If dust halos are truly rare in the Kuiper Belt, it could mean these distant objects are tougher, stickier, or more isolated than we thought. Alternatively, Varuna might represent a brief phase in icy bodies' evolution, a fleeting window where rotation hasn't yet outpaced cohesion. Until we observe more of these distant worlds up close, its pristine silence will stand as a reminder. Sometimes what's missing speaks louder than what's there. Varuna's light doesn't just flicker, it occasionally screams. Amid its usual dim glow, astronomers have captured brief, violent surges in brightness, as if someone briefly lit a flare on its surface. These spikes aren't subtle, some clock in at over 10 times the object's normal luminosity, blazing for hours before vanishing as suddenly as they appeared. In a realm where change unfolds over millennia, these outbursts are like camera flashes in a dark room, jarring, inexplicable, and gone before we can fully process them. One leading suspect: solar flares, not from Varuna itself, but from our own sun. When the sun erupts with a particularly violent burst of charged particles, these storms can race across the solar system, washing over distant objects like a tidal wave. If Varuna's surface harbors patches of pristine ice, a well-angled solar strike might transform them into momentary mirrors, reflecting an intense glint back toward Earth. Picture sunlight hitting a frozen lake at just the right angle to blind you for an instant, except here, the lake is billions of miles away, and the sunlight is a storm powerful enough to knock out satellites. But timing creates a problem. These brightness spikes don't consistently align with known solar events, leaving gaps in the theory. That's led some researchers to propose internal causes, specifically outgassing. When pockets of volatile ices like nitrogen or methane warm even slightly, they can explosively transition from solid to gas, jetting skyward in geyser-like plumes. On a world as dark as Varuna, even a modest eruption could loft reflective ice crystals high enough to catch sunlight, creating a temporary brilliance against the gloom. The plumes would quickly dissipate in the vacuum, explaining the spike's fleeting nature. Then there's the instrumentation argument. Observing objects this distant pushes telescopes to their limits, and cosmic noise, stray photons from background stars or passing asteroids, can sometimes masquerade as brightness surges. Even Earth's atmosphere introduces wobble, smearing data in ways that occasionally mimic sudden changes. But this explanation falters when multiple telescopes on different continents and in space simultaneously record the same anomaly. The most tantalizing possibility: we're seeing something entirely new. No known solar system phenomenon perfectly explains these spikes in duration, intensity, or frequency. Could Varuna's dark crust periodically fracture under stress, exposing vast reflective plains before resealing? Might it harbor unstable ices that detonate under unique conditions, like celestial landmines waiting for the right trigger? Each unlikely scenario forces us to confront how little we understand about the violent undercurrents beneath seemingly inert surfaces. What makes these flares so unsettling is their randomness. Unlike predictable comet outbursts or cyclical cryovolcanism, Varuna's spikes follow no discernible pattern, emerging as if governed by a roulette wheel. This capriciousness suggests forces we've yet to quantify, or perhaps a combination of factors converging in ways our models can't yet simulate. Until we park a probe in orbit around this dark enigma, its brilliant outbursts will remain both beacon and riddle, flashing cryptic messages from the edge of the known. Varuna's seasons should unfold with the slow, stately rhythm of a celestial metronome, each lasting decades as the distant world inches along its elliptical path. Yet its surface tells a different story, one where changes arrive not with predictable cosmic timing, but in erratic fits and starts. This disconnect between season and transformation is more than just odd. It's a fundamental violation of how planetary climates ought to behave, suggesting forces at work that we've never encountered before. Start with the basics. At Varuna's distance, sunlight is 1,000 times fainter than on Earth, making seasonal shifts far more subtle. But even in this deep freeze, the 84-year journey around the sun should imprint some pattern. Alternating hemispheres basking in slightly warmer summers, while the other half endures prolonged winters. Instead, observations reveal bright frost patches appearing and vanishing out of sync, dark regions shifting without regard to solar exposure, and temperature fluctuations that look more like a chaotic heartbeat than a seasonal tide. The culprit might be Varuna's extreme axial tilt, that same lopsided spin that leaves it rolling like a wayward billiard ball. While Earth's modest 23-degree tilt creates orderly seasons, Varuna's near 90-degree slant could send sunlight skimming across its surface in bizarre, unpredictable ways. Picture a flashlight held sideways over a grapefruit. Some areas get prolonged glare, others none at all, with minor orbital wobbles dramatically redistributing the light. On Varuna, this could create microclimates where pockets of ice sublimate centuries ahead of schedule, while neighboring zones remain frozen in perpetual shadow. Then there's the wild card of its elliptical orbit. Most planets and dwarf planets trace near circular paths, ensuring steady solar input. Varuna's path, however, is stretched like a rubber band, bringing it alternately closer to and farther from the Sun in a cycle spanning centuries. At perihelion, it receives nearly twice the solar energy as at aphelion, a variation that should overpower seasonal effects. Yet some of its brightest surface changes occur during its chilliest, most distant phases, as if the ground itself is generating activity independent of sunlight. The leading explanation, thermal inertia with a twist. Just as asphalt stays warm long after sunset, Varuna's dark, porous crust may absorb and irradiate heat on timescales that defy simple models. But unlike Earth materials, its carbon-rich surface likely conducts heat unevenly, some patches releasing energy quickly, others hoarding it for millennia. This would create a patchwork of delayed reactions where summer thawing in one region might trigger surface changes only when winter has theoretically begun elsewhere. The most intriguing possibility involves chemistry. Certain ice mixtures like ammonia hydrates or methane clathrates undergo phase changes at specific temperatures, releasing or absorbing heat in bursts rather than gradual shifts. If Varuna's subsurface contains pockets of these switch-like materials, they could be flipping states in response to tiny thermal nudges, unleashing sudden geysers or frost deposits that mock traditional seasonal expectations. It's the difference between a glacier melting steadily and a volatile chemical compound detonating when it hits a critical threshold. Yet the real enigma isn't the mechanisms, it's the lack of synchronization. Other tilted, eccentric worlds like Pluto still show some seasonal fidelity. Varuna's refusal to conform suggests an additional player, its rapid rotation. Spinning every 6 hours may churn atmospheric remnants, however thin, or redistribute surface ices fast enough to scramble the solar signal entirely, like a blender turning ordered layers into chaos. What emerges is a picture of a world where season loses earthly meaning, a place where axial tilt, orbital stretch, chemical quirks, and dizzying spin conspire to create weather patterns akin to a slot machine's randomness rather than a conductor's baton. For climatologists, this isn't just a puzzle, it's a revelation that our solar system's outer reaches may harbor meteorological regimes stranger than any fiction, where the very concept of predictability dissolves into the dark. Varuna's chaotic spin and eerie solitude might not be random, they could be the cosmic scars of a shattered partnership. Among the strangest theories about this distant world is that it wasn't always alone, but half of a binary system torn apart by ancient violence. The clues lie in its impossible rotation speed, spinning so fast it should have disintegrated long ago, and the haunting absence of moons where they should logically exist. Could these be the echoes of a celestial breakup so catastrophic it left Varuna whirling like a cosmic figure skater thrown off balance? Binary systems are surprisingly common in the Kuiper Belt. Pluto and Charon are the most famous example, but even smaller objects often travel in pairs, gravitationally bound in eternal dance. For Varuna to have once had a twin wouldn't be unusual, but for that twin to vanish without leaving obvious debris is the real mystery. Computer simulations suggest that if two similarly sized icy bodies orbited each other too closely, gravitational tugs from Neptune or a passing star could have destabilized their dance, sending one spiraling away into the blackness while the other Varuna was left spinning wildly from the recoil. Picture two skaters holding hands in a rapid spin, only for one to suddenly let go, sending the other careening off axis with dizzying speed. The aftermath would have been brutal. The separation would have unleashed enough energy to vaporize any existing moons, either flinging them into space or melting them into temporary rings that eventually fell back onto Varuna's surface. This could explain its moonless state, not because it never had satellites, but because the violence of the split erased them completely. Some models even suggest that the missing companion might not have escaped entirely. It could have disintegrated mid-separation, with parts of it raining back down to create Varuna's elongated shape, like wet clay stretched and deformed by centrifugal force. But the evidence isn't just theoretical. Varuna's rotation fits disturbingly well with binary breakup predictions. Most single objects in the Kuiper Belt spin sedately, completing a rotation every dozen hours or more. Those that do spin faster typically show signs of past collisions, except Varuna's speed is off the charts, matching almost perfectly with simulations of binary systems undergoing catastrophic separation. Even its lopsided shape aligns with this idea, not a clean sphere, but a distorted remnant reshaped by the forces of its own gravitational unraveling. The most chilling possibility, the other half might still be out there. If the binary partner wasn't destroyed but merely flung away, it could still linger in the darkness of the outer solar system, too faint for current telescopes to detect. This would make Varuna a tragic wanderer, perpetually orbiting the ghost of its lost twin, a cosmic Casper haunting the Kuiper Belt's frozen wastes. Yet the binary theory isn't without its skeptics. Some argue that a breakup would have left more debris in orbit, or that Varuna's current path doesn't quite match expected post-separation trajectories. Others counter that time erases evidence. Billions of years of perturbations could have scattered any leftover rings or companion fragments beyond recognition. What makes this mystery so compelling is its sheer scope. If true, Varuna's violent past would rewrite not just its own history, but our understanding of how often such cataclysms shape the Kuiper Belt. Binaries might not just peacefully coexist, they might routinely collide, merge, or tear each other apart in gravitational divorces that leave one partner spinning into oblivion. Varuna's lonely, frenzied dance could be a relic of that chaos, a monument to the solar system's forgotten wars, written in the language of momentum and absence. Until we find its missing half, or definitively prove it never existed, this icy world's erratic spin will keep whispering of a partnership lost to time. Varuna's origin story is a cosmic whodunit with too many suspects and no clear culprit. Every theory about its birthplace comes with a glaring inconsistency, making this distant world one of the solar system's most stubborn cold cases. The most popular suspect, the scattered disk, a chaotic realm of icy bodies flung outward by Neptune's gravitational bullying during the solar system's youth. If Varuna formed there, its wild orbit and peculiar spin could be scars from that violent migration, like a refugee carrying trauma from a war-torn homeland. The math almost adds up until you realize most scattered disk objects share distinct chemical signatures that Varuna conspicuously lacks. Its missing volatiles and dark surface paint it as an outsider in its own supposed neighborhood, like a stranger speaking the wrong dialect in a small village. Then there's the primordial Kuiper Belt theory, the idea that Varuna is a pristine remnant of the solar system's earliest days, chilling undisturbed since birth. This would explain its lack of obvious collision family members and some of its odd surface chemistry. But that calm origin story stumbles when confronted with its extreme spin and lopsided shape. Peacefully formed objects don't typically end up looking like they've been through a cosmic trash compactor. Unless the Kuiper Belt was far more tumultuous than we thought, this theory leaves too many bruises unaccounted for. A third camp argues for a hybrid origin. Varuna might be a stowaway from the inner Oort cloud, gently nudged inward long after the planet settled into place. Its dark, organic, rich crust and absence of fluffy ices align with what we'd expect from that deeper, colder realm. But this invites its own paradox. How did an Oort cloud object end up in such a tidy orbital resonance with Neptune? It's like finding a polar bear in the tropics wearing a perfectly tailored Hawaiian shirt. The darkest horse theory, Varuna isn't a native icy body at all, but a captured centaur, a rogue from the realm of the gas giants that got slingshotted outward. Some centaurs share its inky coloration and rapid rotation, hinting at a possible family connection. But no known centaur matches Varuna's size or density, leaving this theory dangling on thin circumstantial evidence. What makes this mystery so vexing is that every explanation solves one riddle only to create another. If we accept the scattered disk hypothesis, we must explain the missing volatiles. If we embrace the primordial Kuiper Belt idea, we're stuck with the spin problem. Even the wildest theories require bending the laws of physics just enough to make astronomers squirm. The truth might lie in a scenario we haven't even imagined yet, a forgotten chapter of solar system history where the rules we take for granted didn't apply. Until we crack this case, Varuna will remain a cosmic shapeshifter, refusing to fit into any of the boxes we've built for it. Beneath Varuna's dark, fractured crust lies the ultimate cosmic riddle, an interior so alien it might as well belong to another universe. At surface level, this distant world seems frozen in time, but peer deeper, and the rules of physics start to twist. The pressures inside a body this size, especially one spinning fast enough to stretch itself thin, could forge ices harder than steel and fluids denser than magma structures unlike anything in our earthly experience. This isn't just a ball of frozen water and rock, it's a pressure cooker where chemistry takes surreal turns. Imagine descending through Varuna's shell. The first layer might be porous, a brittle lattice of water ice laced with tar-like organics, a fragile skin barely holding together under the strain of its own rotation. But drill deeper and the ice begins to warp. At around 50 kilometers down, the pressure could force molecules into exotic arrangements: ice 2, ice 5, even ice 7 phases where water crystals stack like a mad scientist's origami, some so dense they'd sink in Earth's oceans. These aren't the fragile snowflakes of your childhood winters. They're geologic materials with the rigidity of granite, yet still technically ice. The real enigma starts even farther in. Some models suggest Varuna's core might harbor a hidden ocean, not the sloshing, sunlit seas of Europa, but a thick, briny sludge laced with ammonia or salts, creeping through cracks at temperatures that would flash freeze flesh in seconds. On Earth, antifreeze allows cars to start in winter. On Varuna, similar chemistry might keep microscopic veins of liquid water flowing even in the deep freeze. And where there's liquid, there's potential not for life as we know it, but for processes that could reshape our understanding of geology in the outer solar system. Then there's the wild card, clathrates. These cage-like structures trap gases like methane in icy prisons, forming under extreme pressure. If Varuna's interior hosts vast deposits of these fire ices, they could act as subterranean time capsules, preserving primordial gases from the birth of the solar system. A single fracture might release them in slow-motion explosions, puffing out plumes of ancient atmosphere like a cosmic sigh. But the most tantalizing clue lies in Varuna's gravity field. Those odd fluctuations we've detected, they could hint at caverns of near vacuum hollowed out by escaping volatiles, or conversely, dense metallic nodules sunk toward the core, relics of a violent collision that left behind planetary shrapnel. Picture an avocado with its pit displaced, wobbling unevenly as it spins. Now replace the fruit with a world and the pit with a chunk of some long-dead protoplanet, and you've got a glimpse of the chaos beneath the surface. The only way to solve these mysteries is to go there. Future missions equipped with radar penetrators or seismic sensors could map Varuna's guts in ways telescopes never will. Imagine a lander piercing its dark crust, tasting the chemistry of its ices, or an orbiter tracing gravitational ripples to chart hidden oceans. Each measurement would be a revelation, not just about Varuna, but about the thousands of similar worlds lurking in the Kuiper Belt shadows. Until then, this distant enigma keeps its secrets locked under ice that defies imagination, a reminder that even in the farthest reaches of our solar system, the most profound discoveries don't always glitter on the surface. Sometimes they're buried deep, waiting for the right moment and the right probe to crack them open. Varuna stands as one of the most enigmatic sentinels in our solar system, a world that defies explanation at every turn. From its bizarre, football-like shape to the eerie absence of moons, from its inexplicable thermal anomalies to the ghostly whispers of a lost binary partner, each mystery peels back another layer of cosmic intrigue. Why does it spin so fast it should tear itself apart? What hides beneath its pitch-black surface? Exotic minerals, underground oceans, or caverns of near vacuum? Why does its light flicker unpredictably, as if something beneath the ice is stirring? These aren't just curiosities, they're profound cracks in our understanding of how distant worlds behave. Consider the contradictions. Varuna's surface is darker than coal, yet dotted with inexplicable bright patches that come and go like cosmic fireflies. Its gravity tugs in ways that suggest a lopsided interior, perhaps denser in some regions, hollow in others, as if its very core is a patchwork of solar system relics. It whips around the sun in sync with Neptune, locked in a gravitational dance that shouldn't have survived billions of years of cosmic chaos. And then there are the violent possibilities. Was it scarred by a cataclysm that left it spinning like a top, or did it once have a twin torn away in some ancient celestial divorce? Even Varuna's silence speaks volumes. Most objects its size broadcast faint radio emissions, but this distant world remains electromagnetically mute, as if wrapped in an invisible shield. Its density readings conflict, its chemistry defies categorization, and its seasons refuse to follow predictable patterns. Every time we think we've pinned it down, Varuna throws another curveball: thermal spikes where none should exist, gravitational quirks that hint at buried voids or dense metallic fragments, and spectral signatures that suggest materials we've never seen before in the Kuiper Belt. These mysteries aren't isolated puzzles, they're interconnected clues to a larger truth about the outer solar system. Varuna's erratic behavior challenges our assumptions about how icy worlds form, evolve, and interact. Is it a lone oddball, or are there others like it lurking in the darkness? Could its contradictions rewrite the story of planetary migration, or even hint at undiscovered forces at work in the frozen reaches beyond Neptune? The most thrilling part: we've only scratched the surface. Every unanswered question about Varuna is an invitation to explore, to question, to imagine. What lies hidden in its shadows? What stories does its crooked spin and battered surface hold? The universe is vast, and for every mystery we solve, a dozen more emerge from the void. Varuna reminds us that discovery isn't just about finding answers, it's about learning to ask better questions. So keep looking up, stay curious, and remember, the greatest adventures in science begin with a single, tantalizing whisper from the unknown.